Merci beaucoup, Marc.
Okay, thank you very much, Freddy. Yeah, indeed. So it's not about energy forecasting, but this is going to be about the revolution in numerical weather forecast and other types of tools, which of course are used in energy forecasting, but also it's going to become a cheap and accessible tool with a lot of uncertainty quantification computation that will become, I mean, very easy to carry out. So there is a lot of things to maybe to get from this talk and be useful later for energy forecasting. So I'm going to speak about this revolution in numerical weather forecast with the use of artificial intelligence tools or machine learning tools. So mostly for learning the dynamics of the atmosphere, and so make forecast. So and having a surrogate or a substitute for the classical physical models that are usually derived from the physical equations, from the Navier-Stokes equations. But I will also talk about the data, because data is critical in forecasting in numerical weather forecast, because this is a chaotic system and you constantly need to actually update the state of the system, because it would diverge from any however good estimation you would have on the system. So it is critical to actually have also observations. So this is also a topic I will be speaking about. And I will be I will give a general overview of what has happened. Maybe not over the past, let's say, 4 months, because I mean, things are going very, very fast. But there were the summer vacation, and I did not really update everything. So I will speak. So I will give this overview of what happened over the past, let's say, 2.5 years in the past. And then I will illustrate some of the very interesting points on issue that we still have with those machine learning surrogate of the weather. And I will illustrate with some of the research that we actually did in the lab. Okay, so I'll start. I'll start with just reminding you of, there won't be any almost no questions. So I will just telling you about the problems that we are dealing with. And the idea is to use machine learning tools, and especially deep learning tools, so a neural network, to actually represent the dynamics of the model of the system that you're observing. So typically here the atmosphere. And so you assume that you have a large database of observations of the dynamical system you're looking at, and you want to predict the forecast from time step tk to time step tk plus 1 or tk minus 1 to tk. And so y is the vector of all the observation that you have on the system. And so this is possibly a gridded state of the system. And M is any model that depends on a set of parameters. So in the case of machine learning, typically we are looking at a large neural network, and the parameters are the weight and basis of your neural network. And so this is typically what they call in machine learning the loss function, and you optimize over the set of parameters and using this large database of observation that you have on the physical system you're looking at. So one thing that I'm not going to discuss much here is the fact that actually in real geophysical systems, so typically the atmosphere, those YK are actually very noisy observation, even though you have millions or dozens of millions of observations every 6 hours in numerical weather forecasting at global scale. Still, those are very noisy. They are meant to be noisy observations compared to engineering standards, for instance. So that actually minimizing such a loss function, would potentially fail. So we have worked on a way to deal with that, and this is doable. But the thing is that the example that I'm going to look at, and in particular the revolution that happened over the past 2.5 years in numerical weather forecast, does not necessarily suffer from this problem yet, because they are using already product very refined and an improved product of the observation on the state of the system. So I'll tell you more about that later on. That most of you know actually, but that's for the audience. Okay, so I'm skipping this. Just to tell you the kind of on a low-order model. So this is a typical low-order model for chaotic system. This is a one-dimensional one called the Kuromoto-Shevardnadze model. It's a very first one for people working on dynamical system. And you learn, so you typically learn the, you have a long trajectory and you observe this trajectory. This is this reference trajectory, for instance, and you have a very long one, and you use the loss function that I've shown earlier to try to learn the underlying dynamics. And so as to replace the usual PDE that you have here for the model that you discretize and you got a numerical model. Instead of that, you use this neural network and you learn all the weight and biases of this neural network through the loss function that I've shown. And once you've trained this, minimized this loss function, so train your neural network, you end up with the ability to do some forecast with this neural network. And this is typically if you start from the same initial state for the true model, or the one that you integrate knowing exactly the equations and the surrogate. So you end up having those two trajectories, and this is the difference. So this is the error between the two trajectories. Because this is a typical chaotic dynamics, like the atmosphere, the ocean, the climate, this is chaotic. So no matter how good your model is, even though it's numerically almost the same as the ground truth, you will have a divergence at some point between the two trajectories because the system is chaotic. So this is expected, and of course, so forecasting at 6 Lyapunov time, for those who know this kind of measure in dynamical system, this is very, very good. So 1 Lyapunov time would be typically in the atmosphere 2 days. So that would be like 12 days. So that would be very fine. Okay, so why do we need? So why would we need to actually instead of just playing? I mean, okay, playing with that and building machine learning models, machine learning emulator is a very nice thing per se. But then, I mean, are there very reasons why that could be very useful, and why are people really interested in that? So the first thing is, of course, that those AI model or those neural network, can run on GPU and TPU, and it's super fast. They could be, tens, hundreds, thousands, tens of thousands faster than actually running the physical model running on CPUs. So this is the first main advantage. And there is the fact that this is much easier for us, for researchers or practitioners, to actually use those tools because those are connected to those deep learning libraries that are coded by Google, Facebook, NVIDIA, and so on, that are very convenient. Most of them built on, they are not written in, but they are built on Python. We can use them from Python, so that's very, very easy. And they would easily use that computation on the GPUs, TPUs, and parallelization would be trivial for us. So that's an extremely convenient tool. The other thing that makes them extremely attractive and appealing for researchers and the practitioners is the fact that those neural networks that are built with those libraries and many of the variants that they have are actually auto-differentiable, meaning that you can actually automatically compute the gradient or the tangent linear and the adjoint of those models. And this is really, really something very important because this has been the bottleneck of the what we call data assimilation. So that was a very technique, very important for numerical model forecasting. And the thing is that there was always been this issue of being able to compute the gradient of a loss function, and like in optimal control, to be able to actually use and leverage the adjoint, the tangent linear and adjoint of the evolution model, and that was always been a very difficult subject. This is also a computer science theoretical subject. And this is a solution. Those are surrogates, so this is not necessarily the exact auto-differentiable, I mean, the tangent linear of the original model, but still, this is really viable solutions to compute and to have the, so now we assume that we have the tangent linear and a joint of those surrogate models, meaning that you can actually do a lot of optimization with those models. Whatever you try to optimize, so like in data simulation, if this is optimizing the trajectory, or if you want to optimize any product, any yield, anything in for instance, for energy forecasting, you can go, if those loss function depends, or the cost function depends on the model, then you can differentiate through the model thanks to those surrogates. So that is very, very important. And this really lifts a bottleneck that we had for 30 years, I guess. And the other thing, because they are fast, it also allows to do a lot of ensemble forecasting, meaning instead of the like the 50 members that numerical weather centers add in their ensemble forecast, now they will be able to actually run like thousands of ensemble forecasts with thousands of members or more, thanks to those surrogate models. So that is why this is so appealing and attractive. Okay, so a bit of what happened, a bit of history of what happened over the past 2 years and a half. So I mean, it certainly was in the air, and I remember that we were already thinking about it, and a lot of people were thinking about it. But there is so Geissler almost on his free time is I think he was working with Google but on his free time he did try to apply so optimize this loss function and apply this to so infer a numerical weather forecast model, but using the database known as the reanalysis database known as ERA5, so that most of you know. But this is a complete reanalysis of the weather over the several decades, and this database, I mean, this is critical. So this reanalysis database actually comes from it has been derived from the knowledge of the physical model called the IFS at the European Center. It's been also obtained through the use of data assimilation and a lot of observations over these decades of time. So this is the output. This is the best possible output that you can actually generate from data assimilation, the use of the IFS and the observations on the Earth. And so this leads to those several reanalysis products. And the one that is available and the most accurate one that is available is called ERA5. And so Geissler actually trained on the ERA5 at some already quite high resolution. He trained his neural network, and actually it was a graph neural network, and he'd obtained already very, very promising results, meaning that he was actually able to emulate the IFS at a rather fine resolution. It was not the finest one at the time, but it was quite fine already. And then NVIDIA also jumped into the game, and it leads to NVIDIA ForecastNet, I mean, now being even better. And then several Chinese players also, and one of them is Huawei Pengu Weather, which went even better and was getting closer to what the European Center was able to achieve with the best non-model physical model in the world, known as I said, the IFS, Integrated Forecasting System. And then Google also, now officially Google, and this time this is Google DeepMind, so because there are two groups in Google actually working on that kind of subject. So Google DeepMind in London, they have again a graph neural network, so which is called GraphCast. And then they now achieved, or they claim that they achieved at the time performance, so scores that are as good as, if better, than the one which is achieved with the IFS at the ECMWF. So I think the claim was a bit too much at the time, But you'll see that now it's actually not necessarily a bad claim. And Microsoft came also into the game with Climax, but Climax is actually a foundational model. It's a foundation model, meaning that it's a multi-purpose surrogate model of the atmosphere or at several scales. So it's not really in competition directly for the numerical weather forecast, but this is something slightly different, could be used as a climate model as well. And then maybe I can point to Google's Neural GCM. So this is Neural GCM is the name of the model, and now this is slightly different because instead of learning the full model with your neural network, you want to leverage the knowledge that you have on the physics, and especially on the dynamics of the atmosphere, which is the Navier-Stokes equation. So all the motions, you want to stick to the code that you have and the ability to discretize the PDEs. But this is rather well known. You can actually code it very easily and use JAX to make it auto-differentiable. So this well-known part of the model, of the numerical weather forecast model, is actually coded from the PDEs. And all the rest, the physics, what happened over a column in the numerical weather forecast model, the deep convections, and many other schemes that are much more difficult to actually represent physically because you would need subgrid parametrization and things like that. This actually is addressed by a neural network. So this is called an hybrid approach where you mix a physical model with a neural network. So this is called Neural GCM. And then there is another one, so I will speak about this. This is one of the things that I'm going to illustrate. So this hybrid approach. And then there is another thing which is called a GenCast model, where instead of having a deterministic model, surrogate model, you want to generate a stochastic and a generative actually model, something which is closer to generative AI, where we actually want to generate an ensemble of trajectory rather than just a deterministic trajectory for your system. And this is called GenCast, and I will go over it a little bit because I will also illustrate this with something we did. Now, today, so those are contributions, very competitive distribution, but the European Center, which is really one of the very best, if not the best center, numerical weather center and forecasting center in the world, and actually they did anticipate very well what was going to happen, and so they are now using those tools, not to make the operational forecast. They are still relying on the IFS and the observations and simulation, but they are running in parallel those surrogate models to test and evaluate. And they have their own surrogate model from AI, which is forked from Google's GraphCast, and which is called the AIFS. Okay, and those are typical. You can go to the ECMWF website, and you will see all the runs of the AIFS, but also of all those surrogate models. Several of those surrogate models, those that are open source, that are no open source, like typically GraphCast or Pangu Weather. And so you can actually compare, you can make forecasts and compare what are the slight difference that appears over time when making the forecast. Is it really? Yeah. The IFS is made open source. Okay. But it's been But the code maybe But the physics has already made very clear and open because there is always there's a lot of basis of archive from the ECMWF where you can actually read out all the equations that they implemented. There are proper documentations for the code. But no, I didn't know that they made that open as well. Okay, so now that they achieve scores that are. Then it starts depending on the metrics because we are going in final details. But the scores that they can achieve are now as good as the one that the IFS achieves and can be sometimes better. Okay. And those are typical scores that we, and actually, depending on the resolution that you want to achieve, and that's something you can do yourself. So using those, the ERA5 database, and they are actually derived product available to the community that you can easily access, and you can download the dataset in a very nicely implemented way, so that it's actually easy for any researcher to actually implement his own loss function and then train his own model, and so that's something we can do, and we did that like 2 years ago, but it's at coarse resolution because we intended to run that on a single GPU and then not use a farm of GPU for the training. So that's something you can do as well if you want. So what are the limitations of those models? So what they achieve are very good, extremely good, almost as good, if not better, than the best model in the world. Okay, so but still we have to be aware of their limitations. And for the most important one is the fact that they all rely on this reanalysis data set, and especially ERA5. And as I mentioned, ERA5 has been obtained from the IFS, from the data simulation, and a lot of observations. Okay, so yeah, if you still want to improve those surrogate models, you are stuck because we know that we can't really. It's difficult to use them later on to overtrain, because then it would lead to impoverishment of the database and probably degradation of the results. So there is a bottleneck here in the sense that they still all rely on the ERA5 data set. So at the time when I first wrote those slides, like 2 years ago, not all the codes were public, but most of the GAFA's actually surrogate models have been made public and are accessible, and that's the reason why DCMWF are actually running them, because actually you can check and access them. Now, they are one of the first caveats that has been discussed for those models is the fact that they tend to, as you forecast those surrogate models, over a few days, they tend to smooth out all the details of metrology. They are extremely efficient at the very beginning, and then they tend to smooth out all the details. All of the structure, whatever you've got, so for temperature, that's fine because it's relatively smooth, but for the winds, for instance, or for humidity, you've got a lot of details in the forecasted fields, meteorological fields, that you will be smoothed out by those surrogate models. And yet, the scores are better. So that's the typical issues or typical consequences of the fact that we've trained them with an L2 norm. Okay, and so that effectively it's the mean of the forecast that is actually meant to be the most accurate forecast in terms of root mean square error. It's the mean of the forecast or not an individual member of the forecast, meaning that actually what the model trains is trained to learn is something which is not necessarily physical on the long term, but something which is very good at getting a very good root mean square error. So at some point, it diverged from this goal, which is to get a very good physical model. It's not a physical model anymore. It's just a model which gives you fields that are very good in terms of root mean square error. And so that's the first issue. And there are other issues, consistency issue, like geostrophic balance and the vertical wind, which are not correct. And this is discussed, for instance, in a paper by Massimo Bonavita. So there are several issues, physical issues that you have to be aware when you use those surrogate models. Okay, so I'm going to illustrate, give 2 illustrations of what we actually did. First one is about hybrid modeling. So, in parallel to this neural GCM approach of Google, so not Google DeepMind, but Google from San Francisco, the other group, where they had this nice implementation, auto-differentiable physical implementation of the transport in the weather model, and the rest of the physics is implemented with a neural network. It turns out that this is something that we've been planning and doing over the past 3 or 4 years with DCMWF. We've been doing that with them. So our physical model actually will be the IFS. so the full EIFS that we know, and we actually know the adjoint of the EIFS, which has been computed by hand. And we add some neural network to actually try to correct. So it's more like error model correction. We try to correct what's happening in the column actually of the IFS. Try to correct for this, typically this deep convection, something which won't be necessarily very well addressed by the model. And this leads to this hybrid model. And we want to train through this this hybrid model. We will, from this loss function, and actually from the loss function of data assimilation, we want to improve the weight and optimize the weight and biases of the neural network part of this hybrid model, and try to estimate this model error. So, in effect, try to improve the IFS. And okay, so there was a few technical issues. The first one being that the IFS is in Fortran, so. And we have to since we want to train everything all together in a seamless way, so we had to actually code our own deep learning library in Fortran for that, and that's what we did. But we have a very focused need, so we didn't have to implement the full library, but just the type of structure or architecture that we wanted to. And the second key ingredient was actually to insert the learning scheme. So this loss function now would be more complicated. But it was very essential to have it actually trained, but taking into account the whole system of the IFS, I mean, around the IFS for making data assimilation of the IFS. And you have, of course, you can't force those people in the operational centers, and especially the best one in the world, to actually change everything. They will never have time. They don't have the, I mean, they don't have the luxury to do so. So you have to completely adapt, and this is what we did. So the learning scheme, we went to actually the kind of data assimilation method that they had, and we adapt their method so that we could learn actually this neural network corrections to the IFS. So typically you see a kind of code that represents the data assimilation method, the one that is actually run operationally at the European Center, and the red lines are actually those lines that were required to learn the neural network. So you see that it's a minimal change in their algorithm, in their network, in their code, to actually be able to train this neural network, this model error correction to the IFS. And this is exactly what was implemented. Okay. And typically the architectures. The architecture that we had was this, it's a column one. So instead of having a full 3D neural network that represents the full 3D physics, this is only the column that we're actually trying to improve upon. But of course, it depends on the latitude, longitude. So there are some, and time. So there are some time and space dependence of the column. But really, it's the physics happening in the vertical that actually we are interested in. And that, of course, makes the training much more simpler and faster. Okay, so that's the kind of results that we typically obtain with this hybrid model. The important thing is that there are two ways to actually train, learn, and improve this neural network to correct the IFS. The first one is offline. So as we usually, most people do, actually, we learn from a large database, let's say several years. This is what we did, several years of meteorology. And now those were the analysis and operational forecast. So we trained from this few years of meteorology. And you do that completely offline, completely disconnected from what's happening at the present. And you end up with having an optimized neural network that you can try and make forecasts with this correction of the IFS and make some tests of how good it is. And this is where we get some reduction in the root mean square error, typically of 1 to 2%, which is actually huge in meteorology because those are hypertuned models and hypertuned system. So a few percent actually improvement is a big deal. Of course, they have to be systematic, but or on average, but you have to prove that. But if this is the case, then it's fine. But the other way to actually train that is online. And by online here, I mean that we instead of doing a whole, you start from a correction, a neural network that has been pre-trained, But then afterwards, as you receive new observations, like we do in operational centers when forecasting and doing data assimilation, so typically every 6 hours you receive a lot of observations that you use to correct the trajectory thanks to data assimilation of the IFS. But instead of correcting only the trajectory, as it's done every day in every operational centers in the world, you also correct the neural network that is accounting for the model error. Okay, so this is a completely online correction scheme where you keep trying to improve the model error correction. Okay, and that is actually hasn't been done by any other group, even those Google stuff. They didn't, and so this is something which has been assessed. I mean, and we still get a lot of improvement from that, but we are still trying to implement how robust this is, and but this is something underway. Okay, so you got a lot of results. I mean, this is especially good in the stratosphere. I mean, this is the blue thing that you see at the top of the atmosphere, and this is just due to the fact that we know that there is a major bias of the IFS that is corrected by the data assimilation, but there is a major bias in the IFS in the stratosphere, and so the neural network actually corrects for that very naturally. So that was expected, and this is what happened, which is good. Okay, now let's talk about the other thing, the fact that those surrogate models have the tendency to smooth out the fields that they predict over several days. The more you autoregressively run them or roll out at the same machine learning, the more smooth the fields are going to become, because those are the best fields that are required to have a good least square error on the long term, but they are not physical. Okay. So this is something that we have addressed through a project actually where we are not working on numerical weather forecast, but on sea ice modeling and building surrogate models of sea ice. So it's been the PhD thesis of Charlotte Durand, and she's been building a surrogate model for the Arctic, and she's been learning that from a known model, which is called NextSim. So an advanced model of sea ice, especially in the Arctic, and it's a physical model, and we learn from snapshot of this physical model, and we learn this surrogate model that Charlotte trained and then validated and tested and validated. So that's typical. Those are typical examples of. So on the left, this is NextSim, and on the right, this is several weeks actually forecast of the surrogate model that is built on NextSim. And you see how smooth out actually this became, those fields for sea ice. So this is sea ice thickness here, I guess. Yeah, and yes, Epaisseur, okay. So this is, you see that all those flows, those small details here are not present anymore. This is really smooth out, so you are losing in a lot of details. And this is because of this effect, which is, so sea ice forecasting is even more difficult. I mean, even though it's two-dimensional, that's the nice thing. The rest is actually more difficult at weather forecasting because it's highly anisotropic, it's multifractal. There's a lot of things that are, I mean, there is a rheology, it's chaotic, there is a rheology, complex rheology, so there are a lot of things that makes things very difficult. And it's very anisotropic, which is, so that's not so easy. And still, it captures all the advection, all the part which is smooth is extremely well captured. So all the motion actually of the Arctic sheet is actually very well modeled predicted by the surrogate, and the surrogate is actually stable over a couple of years. So that's at least as a deterministic model, this is good, except that it smooths out the details. Okay, so this is something that. Tobias Finn, which is postdoc on this SASIP project, on this CICE project, he has been working on also building more recently his own emulators, surrogate and using a neural network, but also not only looking at CIs, but also several other variables in the model. So it's a multivariate model. And it was also looking at addressing this issue of this smoothing, this over-smoothing that we have, because the intention, ultimately, would be actually to get a surrogate model that would be more physical. Even though it would be not as good in terms of root mean square error, it could be better in terms of ensemble forecast error. So this is his own version of the deterministic model. But now he's looking as, instead of having a deterministic model, he's looking at a stochastic model. Okay, something that would be a model that will actually address, where's the, okay. A model that instead of just predicting from a state what should be the next state, all the potential states, okay, whose mean would still be a very good field for root mean square error, but the mean of this ensemble wouldn't necessarily be physical, although the members of this ensemble could be physical. Okay, so it's in the mathematically speaking, it's really a stochastic model. Okay, with a deterministic part and something where with noise that would generate all those details in the model. And so that's the architecture typically that we use. It's a U-Net, as we saw this afternoon. This is a U-Net, but also there is a transformer part at the core at the bottom of this U-Net. So it's a rather big model. And this is built on this. This model is built from this this revolution. It's deep learning, called generative AI, where we talk about the GAN, where you could use the GAN or diffusion models to actually sample from a distribution typically new faces of people, and inventing new faces, and starting from noise and then generating new faces of people and on any other thing. So it's a generative tool, not these deterministic connections with machine learning, which is much simpler. No, it's really a deterministic tool. In terms of dynamical system, this corresponds to a stochastic dynamical system or surrogate model that you would like to learn.
May I ask you a question? Here you think of part of a model making the prediction for the deterministic part and the part of the model making the generation of this dispersion as two independent bits, or? No,
in this with the diffusion model, so that's something you could do, and this is usually what is traditionally done in ensemble forecasting in the geosciences, so especially in numerical weather forecast, where people would have then a deterministic part plus a way to generate physical perturbation on top of that. Here, with the diffusion, you actually you don't have this deterministic part. The deterministic part would be obtained only later on by averaging. So here, those are really an ensemble that you generate. Yeah. You're right. So in a nutshell, what is this diffusion model and how does it? So it's much easier to train than a GAN. It's also in the end more efficient. So that's what people have shifted from GAN to diffusion model. And the idea is to start from a sample, any sample of a distribution. So those are sea ice fields, sea ice thickness field actually. Yeah, okay, those on the left, and then you add noise, typically a random Gaussian noise, and you blur the image. You progressively blur actually the image, or blur or add noise, actually white noise on the image, so that at the end of the day, it's really completely noise in the image. And the idea is to try. So you are moving from the initial PDF to the Gaussian PDF. And the idea is to try to learn, to actually move backwards, step by step, from Gaussian distributions to the target distribution. And what you learn, what you want to learn is actually through the use of a neural network or any machine learning model. Okay, and which will make this denoising of the operation. And so starting with any noise, you have the hope that you will end up with a proper member sample of the distribution that you originally worked on. Okay, so if I have, and typically for us, this is a large set of fields of sea ice, and then we would train that and train the denoising, so that at the end we'd be able to, from any 2D sample of noise, we would draw a new sample of sea ice fields, and something that will be seemingly physical, consistent with sea ice physics. Now, the thing which is important here is that this is not unconditional sampling, because we want to, at the end of the day, we want to do something that is not being used in image. We want to use that as a forecasting tool, so a stochastic forecasting tools. So I really had it as a dynamical model. So it depends on the states you want to start from at tk to forecast at time tk plus 1. So it's really a conditional, you are conditioning from a PDF that depends on time. So you need to condition this denoising at a step on the states that you are starting the state at tk. So among the fields that the neural network has to take into account as input, you need to have these initial conditions. And also in the case of CIs, the forcings, like the winds that you may forecast to help learn how the CIs will move. And so those are things that you have to keep in mind, is that we are conditioning actually this learning on the initial state, so as to be able to use this diffusion model as a dynamical stochastic model. Okay, and once you have trained it, you can use it in inference mode. So and have start from the right, you start with any stochastic noise, but then you get condition on one of the initial conditions and the forcings, and then you apply the neural network that you've learned now in an inference mode, so there's nothing to train, and then you end up having the forecast at time tk plus 1. And that gives you a stochastic model. And so those are first looking at the root mean square error scores. And that is, so this is typically the thing that we have not we have not done so to achieve very good score in terms of root mean square error, because this is where we know that this very diffusing surrogate models, deterministic one, will be trained for. So here, this is just a consistency check, and you see that here Tobias has checked that so this is the diffusion model that we've learned, the stochastic one, with only one member, looking at only one member. And you see that it is almost as good as the deterministic model that is trained independently.
What's one number? You compute the score as an average.
Yeah. No, there's no average here. It's just computing. You just make a forecast with only one sample, and you just compute the root mean square error. Of course, you can do that on many time steps so that you get an average, something robust in terms of statistics. But here, this is just with one member. But then if you take 16 member, you've got the score of the diffusion model. So now this is the average of the diffusion model and diffusion member. And then you end up having actually a root mean square error that is better than the deterministic model, which is nice. And this is compared to the persistent, which is still not so bad for CIs, and free drift, where we have only account for the motion of the ice and not the rheology and things like that. But now comes the good part, and the very good part is the one that we build this diffusion model for, and it's looking at the power spectrum, the energy of those models, and so NUXIM is really these physical CIs models that we've trained all our models from. And I think this is the black curve here. And the power spectra of the deterministic models is in blue. And you see this drop. At the small scales, you see this drop in terms of energy of the deterministic model. This is where actually you smooth out all those details. You lose all the details with time. And the red one is the diffusion model, which, as you see, is quite close, actually, to NUXIM. So it keeps all of the details that you want in NUXIM. And those are actually images for several variables. No, sorry, this is only for CI thickness, sorry. So this is NUXIM over several days. So yeah, 12 hours, 7 days, and 50 days. So this is a deterministic model where things are smoothed out after 50 days. And this is still one trajectory of the generative model that keeps those level of details that you get in NUXIM. Okay, and this is something that, and our goal, but it was like 3 months ago, but by now Tobias almost managed to do it, because now it's training a diffusion model is much more costly, and it's also, than a deterministic surrogate model. And so, and scaling up to higher resolution and higher domains actually also much more expensive. This is not something that only applies to us, but it's known in computer vision that scaling up diffusion models is not so easy. And so this is typically the result of his effort, where he tried to scale up to the full Arctic instead of just a local domain in the Arctic. And this is the kind of results that he got. So this is the NextSim. So this is not the same trajectory, but this is a typical trajectory of NextSim for different variables. So CI thickness, the concentration, the speed, and so it's the stress tensor typically. Some measure of the stress tensor. And here, this is the diffusion model. And you see all the levels. So this is not the same trajectory, so it should not compare exactly. But you see the kind of details that are actually kept for all the variables that we are looking at compared to NextSim. Okay, and so the corresponding attempt in numerical weather forecast is this GraphCast from Google that I was mentioning. And this is their diffusion model condition on the initial state, and this is their stochastic variant for numerical weather forecasting. Okay, so to conclude, so now we got these surrogate AI models that are as accurate as the IFS, but they are much faster. So keep in mind that they are actually much faster. But they are learned from this ERA5 database that has been built on the physical model data simulation and a lot of observations. So they are still a major caveat here. We cannot really progress as much as now. We are stuck by this issue of the fact that they train from all the observations from this database, and now unless they invent something new, then or wait for the ERA6, which should actually come soon. There are issues like the smoothing of the fields, and one of the key new developments is generative AI over the past year, and I've shown you an example with CIs. Now there are the fact that if you want to build one of the most exciting things that has been discussed over the past, let's say 2 years, is so now you want to train a full forecasting system, accounting not only for with this forecasting model, but also the full data assimilation scheme, meaning that you would have to use all those observations and make an update of the state of the system. So you have to have a proper forecasting over a long time window of this chaotic system. And again, this is where extending, going further than just the dynamics, we would actually to learn and train a neural network to actually account for the whole process. So it will be that the only input, almost the only input of the neural network would be the observations. And the neural network would infer not only the dynamics, implicitly not only the dynamics, but also the way to account for this observation and ingest all the observations to correct the trajectory of the dynamics. Because the dynamics will be still chaotic. No matter how happens under the hood with the neural network, it's still an unstable dynamics, fundamentally one. So it has to assimilate those observations. And I think that's pretty much what I had to say. So thank you.